We are now ready to calculate and write up the APA-style report for a simple linear regression in JASP. We will be computing a simple linear regression in JASP using the dataset jobsatisfaction.sav, in which an administrator at a mental health clinic was interested in predicting job satisfaction from burnout. These data are from 200 mental health counselors. We will use level of burnout, a loss of enthusiasm for a job, to predict job satisfaction among these counselors. So the predictor, or X value, is burnout, and burnout predicts job satisfaction, which is the Y variable. Theoretically, high levels of burnout would predict low levels of job satisfaction. Before we do this, I'm going to let you in on a little secret. We are doing a simple linear regression with two variables, and that is really the same thing as a correlation. Instead of examining their relationship, as we did with correlation, we're using one to predict the other. But the underlying math is actually the same. In fact, you will see a correlation coefficient as a beta coefficient in our regression. Now, when we use two or more predictors, then things get more interesting. But for now, we're going to use two variables, one predictor, one criterion, and learn the basics of regression. So let's turn to JASP. Once you have JASP open, we will open the dataset by going to our main menu icon. Open, Computer, Desktop. Locate the jobsatisfaction.sav dataset and click Open. Notice that this is actually an SPSS dataset. JASP can open a .sav file directly, as well as CSV datasets, but not an Excel file. Those have to be converted to CSV first. One advantage of using an SPSS dataset is that JASP will also read the variable settings already existing in the file. We see that the variable levels of measurement have been set, and the levels of the factors, like gender and marital status, are also labeled. Now, all tests are built upon assumptions. One of the assumptions for linear regression is that the variables are linearly related. No reason to do a regression if the variables are unrelated or related in some wonky, non-linear way. As we did with correlation, let's begin with a scatterplot to make sure that we have some semblance of a linear relationship between these two variables. To do this, we will use the regression menu and under classical, choose correlation. Move the predictor variable, burnout, first, followed by the criterion or outcome variable, job satisfaction. In the results pane, we already see the correlation appear because JASP uses progressive disclosure. The correlation between these two variables is a negative 0.65. The relationship is negative or inverse, just as we expected, and its strength is a 0.65, a number that ranges between 0 and 1. Now remember that number. That negative 0.65 will appear again. Well, let's display these findings a bit more clearly. Click on Display Pairwise. And there we go, a simple, clean table. But we are here for that scatter plot. Now, easy enough once you see the name under Plots. Let's check the assumptions while we were here. In the scatter plot, the data look linear related and negative, so as burnout increases, job satisfaction decreases. Also, the spread of the data are similar along the regression line. They're not cone-shaped or curved. So we have homoscedasticity and linearity. We do not need to check for collinearity because there is only one predictor variable. Collinearity is when multiple predictors are correlated among themselves, which is of course not a problem when you have only one predictor. Next, click on densities for variables. The resulting histograms show us that both variables appear to be roughly normally distributed. In regression, your dependent variable needs to be normally distributed. Now in this case, we see a lovely normal distribution for job satisfaction. There is no assumption of normality for the predictor variables. But a wonky dependent variable can cause you problems and may need to be transformed. We will also check the normality of the errors or the standardized residuals when we do the regression. This satisfies the assumption of normality. In fact, under assumptions checks, we can even check for pairwise normality using a Shapiro-Wilk test. Because the p-value is non-significant, this assumption has also been met. So overall, these data look good. So now we can proceed with the regression analysis. We will be creating a new analysis here, but we will continue using regression. Under classical, choose linear regression. Because of JASP progressive disclosure, we already see the tables where our results will appear. We're predicting job satisfaction, so that is our dependent variable. The method should be set to enter for this example. Our single predictor is burnout, and that goes in the box labeled covariates. Our results pop up in the results pane. Before we begin interpreting the output, however, we need to check a few more assumptions. As we do that, click on Model. There are no settings that we need right now, but we will adjust the model settings when we do a multiple regression. You can close this for now. Open the Statistics options. We will want to look at the confidence intervals soon, and we need the descriptives. We can get those now. Returning to the assumptions of the test, regression is very sensitive to outliers. We can check for outliers by examining the residual statistics. Click on Statistics. We will look at the standardized residual statistics, which, because they are standardized, can be interpreted like a z-score. The minimum and maximum values for the standardized residuals should not exceed negative 3.29 and positive 3.29 respectively. If they do, you have outliers. Our values are negative 2.6 and positive 2.3, so no outliers. If we had outliers, we would stop now with the interpretation, go back to the data set, examine the scatter plot, and identify the outlier or outliers. You can either delete the entire case, or you can Windsorize the outlier so that it is the same as the next highest non-outlier value in the data set. Of course, if it's a data entry error, you just fix it, and then you would rerun the regression. Okay, good. No outliers. Let's check for independence of observations, which we check by examining the independence of errors using the Durbin-Watson test. The Durbin-Watson statistics are close to 2. Good. We don't want the Durbin-Watson to be less than 1 or greater than 3. So the assumption of independence of observations has also been met. The only other thing to check for is normality. Open the Plots option. We can select the residuals versus histogram for the standardized residuals and add a QQ plot. We will see that our standardized residuals are roughly normally distributed in the histogram. None of the values exceed 3, which confirms that we do not have trouble with outliers. In the QQ plot, the dots generally line up along that 45-degree line, so we have normality of residuals. Tick the residuals versus predicted box. The resulting scatter plot of the standardized residuals versus the predicted values is elliptical, as it should be. So all of the assumptions have been met. The data look great. Nothing to fix or transform. It's almost like I planned it that way when I created this data set. But remember, data act very differently in the wild than they do in captivity, and that is why you need to know how to check test assumptions. And now we can interpret the regression. We will begin our interpretation with the model summary. Do you remember seeing this 0.65 before? Of course, it is a correlation coefficient. You may recall that our variables correlated at a negative 0.65. That is a moderately strong negative correlation. However, for regression, this coefficient will be reported as capital R, and it will always be positive. What is the difference between capital R and lowercase r for reporting? We will be reporting on R using the capital R. But when we wrote up our correlation, we used a lowercase r. That is because we had only one predictor for job satisfaction, or two variables total, in what was called a correlation. Correlations are reported as lowercase r. When we have two or more predictors, such as in multiple regression, we report using capital R. The safe bet is that anytime you're reporting on any type of regression, use capital R. In the model summary, we get some useful information. First, we get R, the correlation of 0.65, which of course we already knew from the correlation matrix. We also get the R squared, 0.423. How do we evaluate this R squared? Remember that we used a lowercase r squared in bivariate correlation as what we called the coefficient of determination. It was the proportion of the variability in the outcome variable that was explained by variability in the predictor variable. Here we have a capital R squared statistic. The R squared statistic is still the coefficient of determination. But in regression, we typically use multiple predictor values to predict an outcome. The capital R squared is the multivariate equivalent of the lowercase r squared from our bivariate correlation. It tells us the proportion of the variance in job satisfaction accounted for by burnout. So here is your interpretation. The R square for this equation was 0.423. That is, 42.3% of the variance in job satisfaction was predictable from level of burnout. Now this is interesting. I thought we were running a linear regression, but here we have this ANOVA summary table. Aren't those two different tests? Remember that regression, ANOVA, Ttest, correlation are all part of the general linear model. So this ANOVA is just another way of looking at our regression model. And what this ANOVA tells us is that our model, with one predictor, works better than simply predicting using the mean. The significance value here means that our model, using burnout as a predictor, was statistically significantly better than prediction without burnout in the model. There is a statistically significant relationship between my predictor and the outcome variable. Burnout is being used to predict job satisfaction. If this ANOVA was not significant, then the predictor that we chose would not contribute to predicting the outcome any better than just using the mean or the intercept. The notes underneath the table tell us that the intercept model has been omitted because it does not provide any meaningful information. And before I interpret the coefficients, let me quickly mention these descriptive statistics. The descriptive statistics will be useful later when we write up the model. We know the means, the standard deviations, and that 200 cases were used in the model. Now we get to the coefficients. Now this is an important box. The ANOVA told us that the model works, but the coefficients will show us how the model works. There are two kinds of coefficients in regression, standardized and unstandardized. The standardized coefficient you can see is negative 0.65. Where have we seen that before? Yes, again, this is a correlation. Correlation is a standardized covariance. But we want to focus on the unstandardized coefficient. These are values that are still in the original units of measurement from our survey. For example, this 235.4 is referring to a score of 235 on our measure of job satisfaction. The null model intercept of 132.165 is a score on the job satisfaction survey, and not just any score. Look at the descriptive statistics. This is the mean of all participants' scores on the job satisfaction measure. And by the way, t-values are the square root of f-values. If you take the square root of this f-value in the ANOVA model for one predictor, you get 12.039, which is the t-value for the single predictor of burnout. What I want you to see is that all of these numbers are answering the same question in various ways. So now we need to find A and B so that we can plug them in and create our regression equation. We don't have any labels for A and B, but both of them are right here in the coefficients table. Remember that A is a constant. In a regression model, that constant is the intercept. So this value is A, 235.459. That is our starting point. The B value is negative 2.11. The B coefficient has a t-value associated with it. This is a t-test to see if adding this variable as a predictor improves the predictive ability of your model. Of course, this would be more useful if we had multiple predictors, some of which were significant and others which were not. If the t-test for a beta coefficient is not statistically significant, then that predictor does not add to your model. If, on the other hand, the t-test is significant, then look at the coefficient. Look at the sign. Is it positive or negative? That tells you whether the dependent variable will increase or decrease due to an increase in the predictor. So, here's how you interpret a coefficient. For every 1 unit increase in the predictor variable, the outcome variable will increase by the unstandardized beta coefficient value. This coefficient is negative, so we read this as, for every 1 unit increase in burnout, job satisfaction will decrease by 2.112 points. The beta would be interpreted as, for every 1 standard deviation increase of burnout, job satisfaction will decrease by 0.65 of a standard deviation. To use our regression equation for prediction, we need to build our regression equation. The form is y equals a minus bx. To use this for prediction, our y changes to a y hat, indicating that this is now a predicted score rather than a measured score. For A, we plug in 235.46 minus B, which is now 2.11. The X is where we can plug in any given predictor value and calculate a predicted Y value. So we will plug in a particular burnout score, and we will predict what will be the job satisfaction score. So let's practice with that. 4 more employees are measured for burnout. What do you predict their job satisfaction scores will be? Using the data in your output, construct a regression equation and plug in these X values. If you would like to try this on your own, feel free to stop the video while you work out these equations. All right, let's see if you got all of these predictions correct. For someone who scored a 25 on the burnout test, you would predict a job satisfaction score of 182.71. For someone who scored 50 on burnout, you would predict 129.96. For someone who scored 70, you would predict 87.76. And for someone who scored 120, you would predict negative 17.74. Now that negative 17 looks a little suspicious. We will talk about that more in the next video about reviewing how to interpret the regression output, but until then, remember our discussion about predicting outside of the range. Here is a sample APA write-up for this bivariate linear regression. We would begin by explaining what test that we used and why we were interested in testing. We could begin with the assumptions of the test and mention how the data satisfied those assumptions, or if the assumptions had been violated. Next, we would report on the model overall to assure that our model predicted better than nothing, and that is what we get from the ANOVA. I probably went into a little more detail than necessary, especially on creating the regression equation, but you should report the confidence intervals and B, or beta, values. Finally, because we did this as part of our in-class study, I wrote up the results from our predictions. You would not typically do this for a journal article. I reported only the valid predictions, not that speculative prediction of 120. And that is how you conduct and report in APA style a simple linear regression using JASP.